Dear all, my name is Danilo D'Angela. I am PhD student in civil engineering at the University of Greenwich, UK. Today I will present a paper entitled Assessment of Fatigue Damage in a Fully Pearlitic Ductile Cast Iron by Evaluation of Acoustic Emission Entropy. The paper is co-authored by my supervisor, Dr. Mariano Ercolino, and by Dr. Costanzo Bellini, Professor Vittorio Di Cocco, and Professor Francesco Iacoviello from the University of Cassino and Southern Lazio. In the first part of the presentation, I will introduce the contents, then I will describe the methods for experimental testing and acoustic emission analysis. In the fourth part, I will describe and show the main results. In the fifth, I'll discuss them, and in the sixth and last, I will trace the conclusions. Ductile cast irons are widely used in civil, industrial, and mechanical engineering. They were obtained in the 40s by adding special elements like magnesium to the preparation and treatment of cast irons. Pipelines and turbines are typical structures made of ductile cast irons, which often undergo fracture and fatigue. Health monitoring allows to mitigate the risk associated with the damage of such structures. On the right of the slide, you can see typical examples of engineering systems and structures made of ductile cast irons. On the top, you can see a pipeline system, and below, some components of engines and wind turbines. Acoustic emission testing, AE testing, is an innovative, passive, non-destructive technique aimed at real-time assessment of structures. On the right, you can see a schematic application of the testing technique. You see the source of the damage that is emitting some energy release which generates acoustic waves. They are detected by the sensor attached to the structure, and they are processed and stored by the acoustic emission instrument. The analysis of the acoustic emission data allows to identify and localize the ongoing damage. The problem is that the traditional approach of the acoustic emission analysis, and you can see an example of a traditional approach plot below, it's often very challenging and complex due to noise disturbance, complexity of material and structures, and chaotic nature of the acoustic phenomenon. So the technique is widely used, but is still challenging. The aim of this study is to assess the application of the acoustic emission technique for real-time monitoring of ductile cast iron structures that are subjected to fatigue loading. Acoustic emission testing of microtensile specimens is performed, and the acoustic emission entropy, according to the Shannon formulation, is carried out in real time. Uniaxial tests on microtensile specimens made of a fully pearlitic ductile cast iron EN GJS 702 are performed. 3 tests are carried out. Test C1 has incremental theta max 200, 300, 400, 500, 600, and 700 megapascal with a theta mean equal to 200 megapascal. So we have a varying R ratio. The test C2 has a fixed theta max 700 megapascal and theta mean 350 megapascal with R that is equal to 0.5. The third and last test is with theta max equal 700 megapascal and theta mean 70 megapascal with R equal to 0.1. You can see the chemical composition of the material. On the left below you can see the microtensile specimen geometry, the tensile holder used in the testing, and the whole tensile testing arrangement. The tensile holder was used because as long as the tests were performed, the specimen together with the tensile holder were removed from the machine in order to perform scanning analysis that actually is not the object of this study. So the whole testing arrangement is presented in the next slide together with the sensors and the acoustic emission system. You can see two sensors were used. One sensor was located very close to the specimen, as you can see here, very close to the red square that is actually representing the tensile holder. Another sensor, sensor number 2, was located on the base, on the steel base of the tensile testing machine. The sensor number 1 was aimed at maximizing the detection of genuine data coming from the actual damage happening within the specimen emission under fatigue testing, while the sensor number 2 was aimed at identifying the patterns of noise caused by vibration and environment disturbance. The two sensors were used simultaneously, and a USB system was considered for the processing and the real-time viewing and the storing of the data. The two sensors have the same dynamic characteristics, and they are resonant at 150 kHz. They were both produced by Mistras Limited. The amplitude threshold was set equal to 45 decibel, and the timing parameters PDT, HDT, HLT were derived by literature studies. A high-pass filter equal to 50 kHz was applied in order to reduce at the minimum the noise background. The acoustic emission analysis was performed according to the evaluation of the Shannon entropy. You can see on the left the equations for the calculation of SE, that is the Shannon entropy. Actually, Pi is representing the vector of the probability distribution of the counts of the acoustic emission. It is recalled that the counts are defined as the times in which the signal exceeded the threshold, as you can see on the figure on the right. So each time the acoustic wave exceeds and goes back the threshold, a count is recorded, and the processing of the counts and the cumulative counts allows the evaluation of the Shannon entropy, as you can see on the left. Let's have a look at the main results of the acoustic emission entropy evaluation. In the big plot, you can see on the left axis the epsilon, that is the strain of the specimens, over the normalized time, where the normalized time is defined by the actual testing time divided by the failure time. So normalized time equal 1 means failure. On the right axis, you can see the time evolution of the logarithmic cumulative Shannon entropy in bits. You see the different three tests have completely different deformation evolution. Obviously, normalizing the time gives a very different perspective of the tests. In particular, the test number 2, C2, it's actually showing a very high number of cycles over the normalized time, which actually doesn't happen with regard to the test 1 and 3 for the different forces of the testing procedure. However, we were interested in the increase of the damage, and we were more interested in the qualitative damage evolution than the single test case. As you can see, despite the different deformation conditions, the entropy trend is very similar among the tests. We have a subvertical branch at the very beginning of the testing, then a gradual knee, and actually we have the slope of the entropy curve is decreasing up to a sub-horizontal section that we can also define as plateau. As you can see, also the value of the entropy at the failure is very similar for the different tests, despite the testing application were particularly different, as you can see. As a result, we can preliminarily say that the entropy trend is very similar, and this actually proves that the entropy is well correlated to the fatigue damage. For example, we can notice that as the damage increases, the slope of the acoustic entropy decreases, as well as a very similar value identified pre-failure condition. This is why actually we applied with a pilot study this approach to a different case application, also considering real-time evaluation of acoustic emission entropy over time discontinuous detection windows. Why time discontinuous detection windows? Because of course we know that the typical monitoring of structures is rarely time continuous over the lifetime of the structure, but actually we can say that each detection window of our model is representative of a real inspection that actually has a very reduced time if compared to the lifetime of the structure. So our protocol, this preliminary protocol that we are defining, is based on the comparison in real time of the current acoustic emission entropy with the previous values according to experimentally established damage criteria. How to establish these criteria? According to the experimental findings. For example, we could use the slope of the acoustic emission entropy as a damage index, as we saw before. So two types of criteria can be defined: timing and alarm criteria. The timing criteria could allow us to define the following inspection. When the following inspection is due, we can look at these timing criteria. These may allow to save time, save time and money, even keeping a high level of safety, because according to the ongoing state of health of the structure, we can define how much time the structure can be without any monitoring. Of course, the more the state of health is critical, the more reduced is the time for the next inspection. The alarm criteria may tell us how is the health state of the structure, and actually can be associated with actions to be undertaken. For example, for the alarm criteria, the value of the threshold threshold value of acoustic emission could be considered as identifying the incipient failure conditions. On the right, you can see a simplified application of the technique. Each vertical subline represents a detection window, and then, as you can see, potential crack onset and definite crack onset match very well the actual crack onset experimentally established, that is actually related to the vertical dashed line. You can see about the 60% of the normalized lifetime, the star that is representing the potential and the definite failure alarms, that actually is predicting the failure about 35–40% of the lifetime earlier than the actual failure that is happening, a normalized lifetime equal to 1. This is just an example to show how promising is this approach. Finally, we can discuss the results and trace the conclusions. We didn't show the results related to the acoustic emission analysis, but we can say that they didn't allow to define univocal damage correlation. This is probably due to the complexity of the material, the noise disturbance, as well as the chaotic nature of the acoustic phenomena. We saw how the trend of the acoustic entropy is regular and similar among the different tests, despite the completely different basic acoustic emission exhibited, as well as the different testing conditions. We found that the fatigue damage is correlated to the acoustic entropy, and the damage criteria might be defined accordingly. We also applied this approach as a pilot study, a study on time discontinuous random monitoring processes, in which actually the detection windows were very reduced. So the monitored life of the structure was very, very small if compared to the lifetime of the structure. This was representative of realistic structural health monitoring of infrastructural systems and other engineering systems. The approach was found to be promising for the assessment of structures that undergo fatigue loading, even though further studies should strengthen the findings as well as extend the evaluation to other case studies. You can find in this slide the references related to the study. Many thanks for your attention. I would be happy to answer your questions in the dedicated section of the conference. I want to conclude thanking my institution, University of Greenwich, and my supervisor, Dr. Mariano Ercolino, as well as the University of Cassino in Southern Lazio that allowed us to perform the mechanical test on the ductile cast irons. Thank you so much again for your attention.